Okay, period 8 physical science. This is the midterm review. Make sure you're not watching the period 6 one, or I should say, if you're in period 6, please don't watch this one. Questions are a little bit different. So I'm going to get right into it. Question 1, I'm going to try to keep the running tally up there, so feel free to fast forward through the parts you don't need to see. Let me grab the right. Alright, number 1. So imagine you took 10 milliliters of each of these 4 liquids and you put them in a beaker, and they split into 4 different layers. How would they look? Well, the idea here is that the lower the density, the more likely it is to float. So the least dense is going to be corn oil. So that's going to be at the very top. The next least dense is going to be water. After that is milk. And after that is maple syrup. Again, the higher the density, the more likely it is to sink. The lower the density, it's going to float. Number 2. What is the density of water? Well, the density of water is 1. And for a unit, it's going to be gram per milliliter. Or you could say 1 gram per centimeter cubed. The idea is it is 1. So things with a greater density than 1 are going to sink. With a lower density than 1 are going to float. Number 3. Which of the 4 substances listed above would sink in water and which would float? Well, as I just said, if it has a less density than 1, it's going to float. So in this case, the only one that's going to float on water is corn oil. Which would sink? Milk and maple syrup, because they're both higher density than 1. Number 4. Formula for density. Density equals mass over volume. Don't forget your density fox. Like that. Mass over volume. Number 5. Particle diagrams. Okay, solid, liquid, and gas. Solid, liquid, gas. Alright, for a solid, for the particles somewhat close together, and you give them one line. I call these the whoosh lines. One line to show that there is some movement there. They're just kind of vibrating in place. For a liquid, we want these spread out a little bit more along the bottom of the container, sort of like that. Okay, and in this case, we give them 2 whoosh lines to show that they're moving a little bit faster than the solids. They're able to kind of glide and slide past one another. And for the gases, we're going to fill this entire container. I'm trying to keep the same number of particles. I think I'm doing 9 each. Now with gases, we give them 4 whoosh lines. We skip right past 3 because it's such a huge jump from liquid into gas that we represent that by doubling the number of whoosh lines. Number 6. Sketch a before and after particle diagram of solids heating up. Alright. So my solid before looks just like it did. Little whoosh lines like that. And when solids heat up, the particles start vibrating a little bit faster, and it ends up spreading apart a little bit more. And that's the key. It's our expansion of solids. So you want to draw it spread out a little more like this. And to show that they are in fact moving faster, let's give it one sort of exaggerated whoosh line like that. Okay, don't give it 2 because 2 we like to represent as a liquid. So 1 exaggerated whoosh line. Number 7, list a real-life example of thermal expansion of solids. One thing you can mention is the bridge gaps. Bridges have little gaps in them, like this, and when you drive over, you hear brr, 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 brr. And the reason those are there is because when it gets really, really hot, that bridge solid is going to expand. It's not really going to expand up that much. It's going to expand side to side. And if those gaps aren't there to allow it to kind of expand into itself, well, it's going to end up buckling and snapping and twisting, and that's definitely not a good thing. So bridge gaps are a good example of solids expanding. Another example you could say is occasionally you'll see railroad buckling. Like if you Google that right now, railroad buckling, you'll see pictures of railroad tracks that kind of swivel. And that happens because they get very hot, they don't have enough room to expand, and they basically twist like that. Another example you could talk about is a lot of people get their ring stuck on their finger, and one way to do it, they say run it under the hot water. Well, you try to run just the metal part under the hot water, the ring is going to heat up. When solids heat up, they expand. That's going to allow the ring to slide off your finger. Number 8. Particle diagram of a liquid heating up. So here's my liquid. I'll do 8. And it's moving with 2 whoosh lines. So again, they're moving enough to kind of glide and slide past one another, but it's not fast enough to totally escape into a gas. And when they heat up, same as with a solid, they're going to expand, they're going to move faster. So let's kind of draw this, expand it a little more like that. And to make it even more clear, we can add like a water level. And in this case, the water level is going to rise. So let's exaggerate our 2 whoosh lines just so that it is in fact moving faster. So that's regular water or cold water compared to hot water. Number 9, real life examples, thermal expansion liquids. One thing you can mention is a thermometer. Basic thermometer like this. The way it works is there's a container inside like that. Okay. And that has some kind of liquid in there. It's usually alcohol, it's not mercury anymore. And when you put this in something warm, this, through conduction of course, this red liquid is going to heat up. And when it heats up, it's going to expand. And alcohol is chosen for these because alcohol expands very much. Even when it heats up a little bit, it's going to expand a lot. So it kind of has 2 options. It can either shatter the glass, which it doesn't do because the glass is pretty strong, or it can rise, and the only place it can expand, and the only place it has to expand is up. So it's going to rise up when you put it in something hot. Just the opposite happens when you put it in something cold. When you put liquids in something cold, or when you cool down liquids, they kind of shrink a little bit, and this liquid's going to shrink back down. Another example you could talk about is sea level rise. Sea level rise is due in some part to ice caps melting, but they need to be the ones that are on land. The ones already floating already displace their weight in water, so those don't actually affect it. It's the ones that are like up on Greenland or on Antarctica. Those do contribute a lot, depending on where you look, 30 to 40%. But most of that sea level rise is due to the simple fact that when water heats up, it expands. So when the oceans heat up a tiny bit, they're going to expand a tiny bit. But if you figure the ocean is several miles deep, that tiny bit they expand is going to could be up to several feet, which would be very bad. Number 10. Which is a higher temperature? A bowl of hot soup or an icy cold pond? This might sound deceptively simple, but it is. Not deceptively, it is simple. Temperature is common sense. Higher temperature means particles are moving around faster. So in this case, it's going to be the bowl of hot soup. And again, that's because temperature is the average speed of the particles. Inside hot soup, the particles are moving around very fast. Higher temperature. Number 11. Which has more heat, the bowl or the pond? In this case, it's going to be the pond, because heat doesn't measure the average speed, it measures like the total movement. So even though the hot soup has all these molecules zipping around super fast, and the pond has all these really slow moving molecules, if you add up like the total amount of movement, the pond's definitely going to have a lot more total movement because there's just so many more molecules in it. So the pond is going to have more total heat even though it's colder. Number 12. What are the boiling points and freezing points of water? In Celsius, 0 for freezing and 100 for boiling. 13 is heat transfer by conduction. That's through direct contact. So if I touch something hot or if I touch something cold, that's heat transfer through conduction. Or you could say you put a pot of boiling water on the top of a stove, direct contact. Or you could say you step outside and wind hits you. Well, wind is just little gas molecules hitting you, physically touching you, and that's conduction. You could say putting a thermometer in hot or cold water, conduction. It's all about direct contact. 14. Convection. Well, convection is the movement of heat upwards through gases or liquids. So let's draw a good example, which is a beaker on a hot plate. Okay, so here's my heat source, and since it's directly touching it, this is conduction right here. And conduction causes the water at the bottom to start heating up as well, because these water molecules hit the hot bottom of the glass. And because basically the water is going to expand a little bit when it heats up, that causes its density to drop, which means it rises up to the top. So that's my hot water going up. And it doesn't really create like a vacuum. Something needs to fill its spot, so cold water rushes in below. This cycle just sort of continues like this, because now this new water down here is going to heat up and rise, and this is now going to sink, and it just goes on forever. So convection cycle inside boiling water is a good example. You could also say the air that rises above a candle or a campfire is another example of convection, because similar to this, gases, when they are hot, they spread out a little bit, and that's going to cause them to rise up. 15. Radiation. Well, classic example is just the sun, which gives off radiation. Radiation is just heat that travels through space in the form of waves. Now when I say space, I don't necessarily just mean outer space, I just mean through the air, through anything. So sunlight is a good example of radiation. Although right now I'm giving off radiation. Heat is flowing out of my body just through space. This light is giving off radiation. Anything that has heat gives off radiation. 16. Fill in the table. Alright, so we have, I hope you guys realize the table continues on the back. Phase changes. First one is done for us, freezing. So next phase change let's talk about is melting. Melting is solid into liquid. So in this case we have slow particles that go from slow to medium speed. In order to do that, they have to pick up energy or absorb energy, so we call that endothermic. Again, they're absorbing, they're pulling in heat. Think endo, pulling in heat. Next phase change we can talk about is vaporization, which is liquid to gas. So liquid is medium, gas is fast. In order to go from medium to fast, again, they have to pull in heat, endothermic. Condensation. Condensation is gas into a liquid. So now we're going from fast to medium. So the particles have to slow down. In order to slow down, they have to dump off their heat. So this is actually going to be exothermic. Exo, releasing heat. He is exiting. The next phase change we can talk about is sublimation. Sublimation is solid directly into a gas. And in this case, we're going from slow to fast, so it has to pick up a lot of heat. Therefore, it has to absorb energy. This is going to be endothermic. Deposition. Deposition is the opposite of sublimation. This is gas directly into a solid. So we're going from fast to slow. In order to do that, it has to dump off a lot of heat all at once. So this is going to be exo, releases its heat. 17. Heating curve of water. So the 5 steps are solid heating up, solid melting into a liquid, liquid heating up, liquid vaporizes into a gas, gas heats up. Okay? And if you want to label these axes, it's temperature and energy or time. So what happens on the plateaus? Here you have solid turning into a liquid, melting, and here you have liquid turning into a gas, vaporization. 18. Cooling curve. We start now in the gas. We have gas cooling down, gas turning into a liquid, liquid cooling down, liquid turning into a solid, solid cooling down. So again, at the plateaus, here we have condensation, gas into liquid, and here we have freezing, liquid into solid. Number 19. Why is Kilimanjaro covered in snow, even though it's on the equator? The answer to this has to do with elevation. The higher up you go, the colder it is. So that's why snow can exist year-round on the top of Mount Kilimanjaro. For the actual scientific reason, we can go a little more deep. It's because at high altitudes, there's less air pressure, meaning there are fewer air molecules that are there to collide. And just like we talked about total heat, the fewer particles you have, the less total heat. So up there, there's a lot less air. There's less particles, less air molecules to transfer that heat through conduction. Number 20. Why does a coastal town tend to have warmer winters than an inland town? Okay, well, it has to do with proximity to water, but let's make sure we're clear on that. So water takes a long time to heat up and a long time to cool down. Instead of time, I should talk about energy. It takes a lot of energy to heat water up. But once that water is hot, it takes a long time and a lot of energy release for that water to cool down. So what happens here, let's start in, which one we got, 20? Let's start in the summer. So by late summer, the ocean has finally caught up to the land, and the ocean's finally warm. You know, the ocean, it starts out pretty cold. You might want to go to the beach in May, but you wouldn't want to go swimming in May. It'd be very cold. So let's say June, July, August, the ocean's finally warm. Well, September, October, November come, and the air starts to cool down, and that causes I shouldn't say the air cools down. It's really the land cools down. You know, the sun comes at less direct angles, so it absorbs less heat. So the land cools down very quickly. We did that lab. We talked about how soil and rocks cool down very quickly compared to water. So by the end of the fall, the earth, the land, is very cold, but the water is still very warm. It still retains its heat from the summer. Okay? So again, you know, it might be chilly, but you could go swimming in like September, October. So the reason that the winter is warmer is because the ocean still holds that residual heat from the last summer for several months into the winter months. And that's why a coastal town is going to be warmer, because some of that heat gets released into that town. 21, similar question, but now it asks the other way. Why does this have a cooler summer? Well, let's just continue that thought. So now, by the end of winter, the ocean has finally cooled down. It took a long time to finally get rid of all that heat. So now the ocean is bitterly cold. February, you know, early January, February, the ocean is very cold. Well, what happens in March, April, May? Well, now the land starts heating up, and it heats up very quickly. But the ocean heats up very slowly. So, you know, by the time May and June roll around, the land is warm, but the ocean is still very cold from the last winter. So what ends up happening is those coastal towns remain a little bit colder because they're right next to the very cold ocean. Let me pause the video there. I'll continue with the next one.